Okay, we are back. Look who we got. We got the guy. We got the star of the show. Okay, we're ready. Okay, yeah, you can just chill right there. All right, we're going to continue talking about thinking like a PhD, like this guy. We should get him a little hat or something, his PhD hat. Oh, he has one actually for the company mascot uh, photo logo. Uh, but I wanted to continue along the lines of the thinking like a PhD. And in this one, I wanted to talk a little bit more about digging into important things that are relevant to maybe whatever it is that you're working on, and making sure that we master the basics. So we've talked about this before, but I hope to kind of give some concrete-ish examples of how I try to do this. And what you want to focus on is probably going to be different, I suspect, than the things that I'm focusing on. But the concepts, I think, of really elevating your thinking are probably going to be similar, no matter what the domain is. So, along those lines, life virtue, I guess it's these things. But in addition to that, our tech virtue is on top of this, digging deep into the important things, this notion of small footsteps in tech every day. And again, the things can be very minor, but what I try to do is learn new things related to technology every day. And even if it's a very small thing, sometimes they're big things, but I try to make sure I find sort of some kind of nugget of new information related to technology every day. Don't always succeed, but I think it's maybe a good goal. And what I find too is this also helps you adopt this sort of perpetual growth mindset where you're conditioning yourself to learn constantly, and so you don't really lose that ability to pick up new skills. It actually, I think, like almost all other skills, it is something that you can learn. Essentially, you can learn how to more effectively learn, and that in and of itself, I think, is a skill. So we'll talk a little bit about that and what that kind of looks like. And then for our company highlight, I wanted to mention FalcorDB. Maybe we'll swing back to them in a moment. Really interesting group of folks. I am connected with Guy and Rohi, their CEO and CTO. I think the world of them. I think I started meeting with them last fall, and really like what they're doing, really impressed with their charter, with their just general goal, and also just super impressed by how amazing technologists they are. So I think they're over yonder. We'll come back to this. Okay. And song, I didn't update the song. Whoops. So I guess we're just going to stay with the fix for a while. And same with my musical frequencies. Looks like I've been a little delinquent. So, bad Goju. Now, with all that stuff out of the way, before we dive in to these important things and mastering the basics, I wanted to quickly cover one of the slides that I share in either the first or second lecture for the course I teach at the university. And this I share with the students to give them an understanding of how I generally teach, and also the forms of critical thinking, the forms of, I think people sometimes call this the knowledge pyramid or the understanding pyramid or something like this. And this isn't from me, but I quite like the way they have this structured, because I think that each level as you go up becomes more advanced. But you often need these lower levels to go to the next level. So the lowest level is just to remember something. In some sense, it's memorization, I guess. Once you've memorized the thing, like what the plus sign looks like, then the next step is to understand what the plus sign actually means. Oh, it means taking two things and adding them together. Then after that, to apply this new information in maybe a new setting. So maybe the example you learned it on is 3 plus 7, and somebody explained that that's 10, and then now it's up to you to do 4 plus 5. So you're going to apply this. And oftentimes what I find is that lower forms of education, and by the way, I don't mean that disrespectfully. I mean that, like, if you were to look at, like, maybe kindergarten through 12th grade, like in the U.S., you might be mostly into this space. You might get a little bit into these two, but you probably don't get into this one. Not in the way that I'll explain. I mean, it's possible, but this one's pretty advanced, and so there's a reason why this is like right at the top. But it's an ordering of things, and I do think that the more mature your reasoning becomes and your general level of cognition, the more you can climb up this pyramid. And so when we're small children, we probably haven't developed the intellectual tools yet to be able to perform this. So we start with this, like memorizing the alphabet or memorizing numbers, memorizing how to spell certain things. And we climb up this ladder and we get to this point, and that's pretty cool. Now, these higher order ones, I think, are things that you'll generally get to when you're at the collegiate level. So undergrad, master's degree, professional doctorates, and PhDs. And to my knowledge, this one here is necessary in most of the programs that I'm familiar with for PhDs. That, let's say, like a tier 1 PhD program, you probably have to demonstrate that you have the ability to create new knowledge, new information that didn't exist before you showed up, at least to the community and your advisors and committees understanding in the area that you're working on. Prior to or outside of the PhD, I'm not sure if you are required to do the creation piece. I think that you are often required to do these other pieces, but, and it's not to say in some cases you wouldn't be doing this. I know that really advanced undergrads can sometimes do undergraduate theses, this type of thing, and I know that some master students will often get like peer-reviewed publications where they're starting to do this, but this is kind of a mandate for the PhD. that if you can't create new information, if you can't create new knowledge, like to actually expand what we know as a species on a particular topic, then most of the tier 1 programs that I'm familiar with won't give you a PhD. And I think that's really the point of most of the PhD programs. It's actually in some ways less about the actual discipline, and it's more about the process that you go through to be able to create new information. Now, what's interesting about this, I think, is that these two pieces here are often critical for us to be able to do this third piece. That it's one thing to know what the plus operator does, or addition, remember what the symbol looks like, understand it, apply it. But then when we start to do the analysis and the evaluation, this is where I think that we can have a bit of a separation. Is people who may be satisfied just with kind of learning a skill and then being able to apply that skill would usually stop here. But those people that want to have like a much deeper understanding will go for these other levels. And what this will allow them to do, at least in my experience, is it allows them to more deeply understand the thing that they're working on. In this case, it's the addition operator, to really analyze this. Like we might analyze this deeply in C++ if we're overloading the binary addition operator. Binary being that it works on two terms, as opposed to like a unary operator, which is just works on a single term, like plus plus x or x minus minus, things like that. So that would be like the analysis part. And then the evaluation part oftentimes is the evaluation potentially in comparison to other things, but oftentimes some sort of scientific evaluation. You're trying to understand parameters of it, like how fast is the addition operator on certain computing architectures? Is it faster on one type of CPU than another? Why is that? Are there limitations? Can you get away with pretty good speed up until you reach some number of operands? Like, let's say there's 10 numbers that you add together and you get certain performance, but once you add that 11th one, then you overload the register files or something and you get a 2x performance reduction. Like, this is sort of the evaluation piece. And when you're doing peer-reviewed publications, you'll often have to do a rigorous evaluation of your thing next to many of the other existing things that are out there. And then the top piece, again, is the creation. So what will often happen is you'll have like the plus operator, right? And so it'll be something like x plus 1. And that's the idea that we're working with. So we remember what that looked like, we understand it, we apply it, we analyze it, we evaluate it, and then we say, wait a second, what if instead of doing x plus 1, we invented a new operator called the plus plus operator? That's not a binary operator, but it's a unary operator. And it has certain benefits that are going to make it superior to using the binary addition. But it also is going to have weaknesses to binary addition. And this is often one of the key pieces with this PhD thinking, is in almost any domain or any method or any kind of thing that I've worked on in this space, of science, I've never experienced a single case where there are not trade-offs. And this is super important because this moves us away from this space of there's one approach that is the best for everything. And instead, there are many approaches, and some of them are effective in some domains, and others are effective in other domains. And the key thing to take away from this is that there are a bunch of things, and they have different strengths and weaknesses. That's one of the most important things to understand. And you will often discuss those things as you do this evaluation. And so when you're creating this new information, this is the topmost piece, because again, you have to deeply understand all of these other pieces before you can sort of trigger that idea of, oh, well, now that I understand all that space of arithmetic and addition, what about this idea? And notice that you can't really, maybe can't's too strong a word, it might be very hard for you to be able to invent new information, new knowledge, without first having a mastery over these pieces. Because if you don't fully understand all the things that are going on in this space, how are you sure that you're creating something that doesn't already exist? And oftentimes we can't know about all the things in the world, right? So I probably know less to nothing in physics. That's not my area. My area is computer science. And so that space, I try to know quite a bit, but then it becomes more and more and more specific, mostly because there's just so many things in the world to know, it's hard to know them all. And so as you become more specific in any of these domains, you can start to gain mastery over this sliver in a more pragmatic way. That if you tried to maybe be the master of 5 domains simultaneously, not to say that it can't be done, I think it can, but you might have to dedicate your life to that charge for decades. And I know that some people have done this, and they have ended up being experts in multiple domains. People like Morris Herlihy, or other mentors that I've worked with who've been doing this kind of stuff for quite some time. So, but if you reel it in and go back to this addition operator, we want to walk all the way up this pyramid and deeply understand all these pieces, and then only once we have all this mastered, then we can do this piece. And the thing that we do with this piece is different than all of this stuff. But in order to do this and actually sort of have some degree of confidence that there is novelty, we have to have all of this stuff like fully locked, which goes back to the point about this being step 2 in thinking like a PhD, is that in order to invent new knowledge, it's my strong conviction that you have to have a very strong mastery over the existing knowledge in that space. Otherwise, you're just talking about stuff that you're not really an expert. And also, that's why the creation pieces last. And now, I know that a lot of people have great ideas and are constantly coming up with new things, new ways for transportation, or a better hamburger or something. And I think that's totally fantastic. But when you're doing sort of like the PhD process, and you really want to have a higher degree of confidence that your contributions are not just kind of like wild claims that can't really be substantiated. Like, I'm going to invent this new bun for a hamburger and it's never been done before. And the amount of time I spent thinking about this is 30 seconds. Now, like, what are the odds that I'm actually going to invent a new hamburger bun that's never been created before? I would speculate that the odds of that are pretty low. And this is also part of the reason why doing a PhD can take so long, is that for the first time, you have to really get all this whole pyramid. Otherwise, you're going to struggle with this. Okay, so I think that we've got this concept down. And this leads me to the next point that I want to make. But before I go on, I want to pause and share something about why this piece that I was explaining, I think, is actually really important, and how it funnels, I think, really concretely to this next piece. And that is this notion of words mattering. That one thing that I see today quite a bit, which kind of makes me a little nervous, if I'm being honest, is the sort of the laissez-faire way that we're communicating, especially on things like social media, where words are being thrown around and things are being said, and people who are ingesting that information, as well as the people that are communicating that information, don't necessarily understand what it is they are actually saying or what they're hearing. And yet they continue to communicate, they continue to speak. And I'm not saying that you should never speak unless you know exactly what it is you're going to say, or you should never write a Twitter post unless it has complete perfect syntax and exactly the right words that you're intending. I don't mean that at all. But what I do mean is that we should, I think, make an effort to try to communicate clearly and ensure minimally that the words that we're saying, the ideas that we're sharing, this type of stuff actually reflects what it is we're trying to convey. And that we're not just sort of saying stuff to sound fancy. And I see this a lot. I see a lot of people these days using words or terms or things, and they don't really know what these things mean, but it maybe sounds fancy. And I think that that can be really dangerous, because it's very hard to have mastery of this pyramid if you don't deeply understand the things that you are communicating or the things that are being communicated to you. But more importantly, it's that the things you're communicating are as close to precisely accurate as you can make them. And again, doing this in spoken form is very hard. Those of us that are on sort of like PhD oral defenses and things like that, we tend to cut people some slack for live settings. I mean, not completely, but a little bit. But for the written, it tends to be much more rigorous in that the written, oftentimes people have time to prepare, and there should be fewer mistakes because they could write it and rewrite it, and they have like lots of opportunity. But the spoken is, because it's real-time-ish, especially if like they're answering questions, that we can lower the bar to some degree. However, that doesn't mean that I think you can just casually say random things that don't make sense. And I would encourage all of you that if sort of thinking like a PhD, or being able to create new knowledge or move technology forward or something of that nature is important to you, if that's important to you, I would say this is maybe one of the first things you should try to master, is that minimally try to make sure that the things that you are saying actually make sense. Let me give you an example. We were in team meeting last week, and I was describing one of the things that Merle's doing and how we're seeing exponential growth in this one area. And as fate would have it, good old Tim Mattson, Dr. Tim Mattson, chimed in and said, was it really exponential growth, Goju? And he was saying that, but he's mostly joking. But I actually stopped and I said, actually, I'm really glad you asked that, because the truth is, I think I misspoke there. So let me try to break this down. And I said, for this one area, I think it isn't right to call it exponential growth. I think it was super linear, or possibly even like polynomial growth, but it wasn't really exponential. However, this second area of growth, this was exponential, at least for the short period, that eventually it'll reach kind of like a saturation point, and then it'll hopefully remain super linear. But right now, it actually, based on the curve that it has, it is like an exponential growth thing. And what I really liked about this is Mattson, as he does, is he's kind of holding me accountable for not saying the wrong words. And most people, I think, would probably just kind of be like, oh yeah, exponential, sure. But what Mattson is doing is he understands exactly what that word means. There's actually a few different definitions of exponential growth, but it's usually this idea that you have some number that then is being increased with some exponentiation. A lot of times people think exponential growth is like a 10x increase, but the truth is, I think actually if you dig a little bit deeper, exponential growth doesn't have to be a 10x growth. It can be like a 2x, but it's something that happens in some constant form, that you're going to continue on that exponential growth for some period of time. So if the number is 2, then it may go to 4, but then it goes to 8, then it goes to 16, then it goes to 32. That's still, I think if I'm getting this right, yeah, because that's still 2 to the increasing on the exponentiation. But it can also mean some number to, or 10 to some number, and that number is increasing. The short version of this is that I actually misspoke there, and Mattson is sort of correctly calling me out, and that's actually good. Now, it may feel like this is hyper pedantic, but I think we should strive to say more precisely what we mean. Now, we're not always going to get this right, but I think the real problem we don't want to have is, the real problem that we want to avoid is that we're not even reasonably close to the thing that we're trying to express. So now let's move away from that exponential thing, and let's go into another area where, let's say I'm talking about the programming languages. And this actually happened once. I was talking with someone, And they were talking about how, back in the day they used to code all the time and they wrote a lot of C+ code. Now, no judgment. I'm not trying to throw this person under the bus, but as I suspect many of you know, I don't know that there's a language called C+, but there is a language called C++. And I don't fault this person at all. But you can see how just this minor thing can potentially degrade someone's credibility, because it may have this appearance of lack of knowledge. And it can be worse when they're not just things where you can intuit the answer and you can be like, well, I think they meant C++. Another example might be someone saying like, yeah, I code in Java all the time. Or I used to code in Java all the time, but they didn't mean Java. They meant JavaScript. Now, those two languages are very different, as I think people that are programmed in both would likely tell you. At least my experience is they're very different. And there's actually a history there on why JavaScript used Java as the first word for their thing. Feel free to Google that, at your own leisure to read up about that. But so now you can imagine that if you are saying something like this, you are confusing your audience, but you're also confusing yourself. And this is why, most importantly, that the things that you're saying, you should try your best to make sure they make sense. And you're not going to get it right all the time. I don't get it right all the time. I like I did in this meeting, I said exponential growth, and the truth is one part of it was not exponential. It was like super linear, and maybe something beyond that, but it wasn't to the magnitude of growth that I was. It was hyperbole, right? I was just exaggerating, not necessarily intending to, but I was being kind of sloppy. And as you go further with the advancement of knowledge and you start to really dig in and become like a very advanced scientist or deep thinker, having precision of language when you're speaking or you're reasoning about things can be hyper important. And it's strange in on one hand, because like I had that life virtue of don't get distracted by the little things. But now I'm actually taking sort of the opposite position, which is really focus on these little things. My argument here is that the little things I was talking about before of not getting distracted by those, these are things like someone cuts you off on the road, someone is rude to you, your food didn't come out at exactly the temperature that you wanted it, and just your favorite shirt is dirty, you couldn't wear it today. Like, these are the little things I think that I would argue don't get distracted by. But when it comes to advancing technology, advancing science, or moving society at large forward, the basics oftentimes I think are the pieces that a lot of people are overlooking because they're too eager to rush to the end. I see this actually quite a bit today with the state of AI and language models, and I've been sort of paying attention to what's going on in this space. And it seems to me that there are a number of startups that are really kind of struggling, which is unfortunate. But a big part of that, it seems to be that they didn't deeply understand language models and the challenges of language models before they kind of went all in. And now they're working in this space that they're slowly starting to learn about, and the rug has been pulled out from underneath them. and in some ways in a very catastrophic fashion. Whereas if they would have had a stronger mastery of the basics, like one of the things that I think most people that has bitten a lot of these early stage language model companies is I don't think they deeply understood the ramifications and complexities associated with language models being stochastic. And not just stochastic in the output of inference, but stochastic in the way that they are training their models, and how that stochasticity can make iterative refinement of the model extremely challenging, which then puts them in a situation where they have a product that maybe is super cool, but then they try to make that product better, yet because it lacks this core principle that it tends to be required for the scientific method, which is determinism, because it lacks this, they really struggle with iterative refinement. Is they can try to make something better, but in the process of trying to make this model better, they break something else, and so they fix one problem and they create 10 new problems. This is a byproduct of stochastic systems, unfortunately. And this is part of the reason why at Merli our core, our foundational tech, our foundational AI is fully deterministic. Is it provides us with this ability to do iterative refinement and make the system better over and over. It doesn't mean that we don't use stochastic pieces in addition to the base technology, which is deterministic, but it does mean that the base technology, that foundational technology, is fully deterministic. So we get the benefits of iterative refinement, which from a scientific perspective, I feel is essential. Okay, so hopefully this makes sense, and hopefully this background will give you something to strive toward if you really want to get this like expert level mastery of something. And it may feel strange that you're spending so much time trying to understand something that's so simple, like what does the word teach actually mean? What does the word exponentiation really mean? And while it may seem that this is hyper pedantic, what I found is that when you go to these base levels and you really start to try to ensure that you have mastery over the most basic primitives, what happens is you start to build yourself a pyramid. Is that this level becomes like fully hardened and it's just like unbreakable. And then you go up another level, and then you spend some time on this level, and then this goes and it does this again, and it becomes really hardened. You don't ever have a layer here where it's sand, right? Or it's something that it's playing cards, because these things really need to be rock solid stone, right? It needs to be this hardened thing, because they're going to support the other levels on top of them. So if any one of these is kind of wavering, if it's flimsy, then this structure that you're building, there's a really good chance it's all going to come crumbling down. And you actually probably see some people that they will get to a certain point in their career, and then they kind of like get found out. And it's like many of the things that people thought they knew, it's like they don't know these things. How does that happen? Well, I think that it's people trying to be smooth talkers and not really spending time mastering the basics, just kind of knowing the words, like, hey, we're going to use LLMs on the cloud in an enterprise system for Web 2.0 or whatever. And so I just said a whole bunch of things, and none of that like even makes any sense. But it may sound fancy. So try to avoid that. Don't get caught in this trap of sounding fancy without saying anything. Instead, strive for sounding simpler. you should oftentimes use the language that's the simplest to explain things, not the most complex. Like, and you can probably see in the things that I write, I try to do this. So, for example, in this step 2, I say dig deep into important things. Why do I use the word things instead of something more fancy? Because things is maybe the simplest word. I could elevate the language. I could do wordsmithing and rewrite this, right? We could sit around and try to make this sound super fancy. So let's say this is step 3. Let's really go overboard here. How about I don't know, something like this. I don't even know what I wrote, but boy, does it sound fancy. Enrich your cerebral and methodological development by compounding temporal qualities of multiple dimensions into iterative mastery over core principles. Wow. That is awful. Like, no. Just no. Also, just as an aside, people often use this word wrong all the time. Generally, you're not even talking about a methodology. Most of the time, you're just talking about a method. Just use the word method. Don't try to sound smart. You should actually try, honestly, one of the keys to unlocking, I think, true mastery over things is to use the simplest words possible. Because the goal, at least for I think people who really want to share information and to learn and to have others learn, the goal of communication is to make things as easy to understand as possible, not as hard to understand as possible. I mean, I often find that the people who have the strongest mastery over subject matters are the ones that can explain it to a 5-year-old. And the ones that don't are the ones that have to write things like this. Because, I don't know, they don't know really what they're saying. And so maybe they read this off of some fortune cookie or something, and they want to sound really smart. Like, don't do that. Don't strong recommend. Don't spend any time trying to sound smart. Do spend time trying to sound precisely correct to help people understand, but not to embellish so you sound cooler, right? Like, so for example, this one, I'm saying emotional detachment from your work. This might sound like these are like 50-cent words. I just couldn't think of simpler words to write here. Maybe there's a better way, but at the time that was the simplest way I could think to write it. And then same thing here. This is kind of the simplest way I could think to write this. Dig deep into important things. I don't know. And then master the basics. I think that's my hope is that most everyone can understand this. And that's my goal, is understanding. I'm not trying to confuse people. I think that's intellectually very dishonest, and I think that it's like sort of the antithesis of what I'm trying to do. on GTT. So hopefully this makes sense about really understanding and saying things that are real, not just using these fluff fillers and saying a whole bunch of stuff and not saying anything. And this can be something that requires some work. I was actually listening to some tech people talking about stuff throughout the week, and there were many of the tech folks that I was talking to, or I was listening to, and like they were saying words, but the words were somewhat nonsensical, and that's not great. And that also is, I don't think, going to get you to this level of being able to think like a PhD. Because thinking like a PhD is that you really are trying to have this mastery of this whole pyramid. Okay, so now, along those lines, I want us to look at Mentor, because I want to give you a concrete demonstration of this, or I'm going to try to. And by the way, I haven't done this. I just thought that I'd try this experiment to try to demonstrate what it looks like when you have mastery of the basics. And I also want to share that this space is a space that matters to me, because this is the type of code that I generally want to work on. This is the code, these are the types of systems that matter to me. And the reason why I'm sharing this is that I'm hoping to impress upon you that when you really have the ability to master the basics, you often will have sort of this innate mastery of a lot of things, or what appears to be a lot of things, but all you've done is just master the basics. You just master the basics, that's it. But it will, to others who have not mastered the basics, it will often look or feel extremely impressive, but it's not. I mean, in my mind, it's not. It's one of the biggest life hacks to actually really get you to be able to create amazing things. And it's not, and the whole purpose of it is not to jump to the end. It's not to create the amazing things. It's not to invent the warp drive. It's to have such strong mastery of the basic things that everything is so simple that you can just kind of like see the future. That's, I think, really the core of it. So what I'm going to do here is I picked this repo. Oh, this is XZ. We were looking at this because of the XZ backdoor exploit in Linux last year. I think it was last year, something like that. And so this is Mentor running on XZ. And so, yeah. And I think too that, it looks like this has been updated. But yeah, it had some comment at one point about Giatan, the bad actor or bad actors that I think are responsible for injecting the backdoor. So anyway, XZ, it's reasonably good. It's part of the Linux Foundation, as I understand it, and it's been around for quite some time. Yeah, there's Gia. Oh yeah, this has been updated since then. Anyway, so now we're going to look at this, and what I want to try to show here is what mastering the basic looks like, and I'm going to try to go through these, and without clicking on the actual anomaly, I'm going to try to explain what each of these expressions is saying just from memory. So just going back to this diagram, and let's see how much I remember, how much I understand, if I can do an application of this, like apply the things that it's saying. Can I analyze this, evaluate? And I'm not going to do creation, I don't think, unless I am rewriting it in my head. But hopefully, if I have good understanding of the basics, I can talk about these things without needing to sort of like have an AI explain it to me, or Google it. And part of the reason why this can be so important, especially in the era of AI systems, is that while I do think AI code generators are getting better, I have a hard time imagining a world where code generators that are generating code based off of things like natural language or something other than code itself. So basically what I'm talking about is it's not code that's being transpiled or augmented that you would do like with a compiler, because this can be super precise, like sort of guaranteed to be behaviorally consistent between the original code and then the new code. So not considering that space, considering the space that you want an AI to write some code for you, which is great, you know, have at it, but then knowing that the AI might get that code wrong, you being able to deeply understand that code, I think is super important to being able to catch the mistakes that the AI is introducing. And this goes back to this whole, there are no shortcuts, that I think if people think you can use an AI code assistant to just get the answer, I don't think so. This is like, this is different than things that might be a one-off where you do it just once. Like, trying to think of a simple example here. Painting your car. That just have somebody do it for you. It doesn't matter for you. And then when it needs to be repainted, you'll repaint it, right? Or someone else will repaint it. But you don't need to understand all the details about painting. I think that there are many cases in the world where that is true. But code, especially for software systems that you're going to try to maintain, I think code is not one of those. I think code is one of those spaces where you probably should know a lot of what's going on. Otherwise, you are probably not going to be able to maintain that code. And AI systems being able to maintain the code that they've written is not necessarily their strong suit, at least not today. And again, being able to do that at scale, I don't know. It's an open question. So having mastery over the basics of code, I think, is going to be critical no matter what happens with the advancement of AI. This is my strong conviction. So, or minimally, it's going to be mastery over critical thinking. But I still think understanding code, because of the working with the machine, that may be a slightly unpopular opinion today, and maybe I can spend a longer podcast talking about why I think that's the case. But the reason why I think this is that I think that, yeah, I think that the AIs are, yeah, it's a deep conversation. I have so many points, essentially, on why I think that coders are not going to go away in the future because of AI. And I think in some cases it's the opposite, that coders will become even more important because the AIs are going to be producing so much code, and now that code needs to be corrected. And the AIs themselves can't do it, because if they could, it would already be correct, right? Like, logically, this kind of makes sense. And so who's going to fix the code that the AIs can't fix? Well, humans. So anyway, let's give this thought experiment a run through. And by the way, I just brought this up. I haven't really practiced this at all. So I don't expect that I'm going to be able to really do this, but let's see how far we can get. Okay, so this first one, we have an if statement, and we're knotting whatever the result is between, it looks like this, I don't know why. Okay, yeah, I changed my mind. Yeah, I do know why. At first I was like, I don't know why you would wrap this whole thing, but now I understand. Is basically you want all of this, whatever the state of this is, to be inverted. So if the outcome of all of this is true, then you invert that and it'll be false. That's what our not is doing here. The other high level point that I see is it looks to me like these are all conjoined by only logical ands, which basically means, I think that that's right, I don't see any logical ors in here. And so that means that all of these conditions have to be true in order for the result here to be true. And so, and if you get that state, then you invert that, it will be false. If any one of these sub-expressions is false, then the outcome of this expression will be true. Because, like, if this first one's false, false ANDed with anything is false. Or the second one, or third one, or fourth one, and so it doesn't matter. That'll be false, and it'll be inverted as true. The other thing that I see is, so we have this opt pointer, and it's looking at these different margins. So left margin, right margin. I don't know what left cont is. Right margin, left margin. Oh, this is, okay. Sorry, this is, okay, yeah, it's getting even more interesting that this is, okay, this is left to margin and left to cont, and right margin. The reason why I'm kind of pausing here is I think it's curious that there's a left to margin, but there's no right to. I don't know if that's by design, but that lack of symmetry raises some eyebrows, at least for me. There's also another thing in here that also raises my pattern detection eye, and it's that you're using the less than operator here throughout this, except for this one. This one is less than or equal to. That's very interesting to me. Maybe that's correct, but I think it's quite interesting. It is literally the only one, but maybe it has to do with the fact that it's this left to margin and this left to cont. Yeah, I'm not sure. But yeah, so that's basically what I think is going on with this. And so all the operators, you have a few comparison operators, less than operator, less than or equal to, less than. You have one unary operator. The not sign is a unary operator. It just works with one operand. So the result of this, whatever it is, it'll just invert that. And then you have opt, which appears to be a pointer, pointing to some field. Now keep in mind, this could potentially be overloaded if it's a class. So it may look like it's a pointer, but it may actually, under the hood, not be that. It could be something else. But that's the general gist of what I get here. So as far as all the symbols that are present here, I think we've discussed all of them. And again, the point of this is to give a demonstration of what mastering the basics looks like, is that I can dissect this and reason about this without any reference material. Why? Because I've spent time on the important things, mastering the basics. Okay, let's try this next one. So input is possible. Okay, buddy, stay right there. Input is possible is not equal to null. Okay, so you want to make sure that this thing actually exists, I take it. And coder mem limit threading minus coder mem in use minus coder out q dot mem in use is greater than or equal to coder mem next block. Okay. All right. Sure. They're just trying to make sure that this space here is greater than this space here, whatever this coder thing is. Yeah. Okay. So I don't know why that's important, but that appears to be what they're looking at. Okay. And this LZMA out Q has buff, and it's taking the address of this coder out Q, so it's essentially making this. So here we can see out Q is an instantiated struct, it looks like, inside of this coder object, and you can tell it's instantiated as part of this because it's not dereferenced through a pointer, it's a dot. And what they're doing here is they're sending the address of this into this function, so they're effectively turning this into a pointer. Yeah, which makes me wonder now. Oh, yeah, I think this is C. I think this is C code. Is that right? Is this C code? Does Mentor not know if this is C code? Hold on. Let's go back to XC. Yeah, okay, it's C code. Oh, that must be a bug. Sorry about that, guys. Yeah, I don't know why it's not showing here. Okay, the reason why I was asking about this, about it being C code, is as I'm looking at this, I was trying to understand why you would pass this in as a pointer rather than just a reference, and I think that it's in old C. I'm not an expert in C. I don't know it as well, I guess, as I know C++. But I think there was a time where it's basically all pointers. They might have references now, but that might be the reason why they're passing the address of this, so you don't do a copy of it. You send the pointer, and then that allows you to potentially change it inside of this function. Or you don't have the copy overhead of the whole struct. So that's what I suspect is going on there. And this check here is just a check on this being a non-zero outcome, whatever this is. So I suspect this is probably just a Boolean. It might be more complicated than that. It might actually be a Boolean that it might be numeric that is actually the buffer size, which would essentially double as true and false. And that if the buffer is 0, then it has no buffer. And if the buffer is non-zero, then it has a side, and you could use the return value as a Boolean to tell you that it has a buffer. So, okay, so that's kind of what's going on in that first piece. And yeah, okay. And then they're taking all of this and then they're ANDing all of this with the result from this piece, and this piece is checking to see if, coder thread initialized is less than these coder threads max, or coder threads free is not equal to null. And they have this stuff wrapped here that basically saying that if this is true or this is true, this will result in true here, And then the overarching outcome is that both sections of this have to be true. So let's go through this again. So this has to be true. This has to be true. This has to be true. And one of these two things has to be true. Yeah, right there. Okay. So, yeah, I think that covers this. I would probably rewrite this. This one I think is, I'm not sure why Mentor is so upset about this. Like, I do think that there's some, I mean, you don't check to see if opt is not equal to null. That's a potential problem. And I thought there was one where it does two indirections. Maybe I'm wrong about that. That's a lot of indirections. And that actually is like a performance thing. Not that we want to go all the way there, but anytime you're invoking the arrow, that pointer indirection is, you might just want to take the dereference of this. Well, okay, that's a longer discussion. Okay, so basically these first two, I think that we understand at least all the symbols, right? There's not a symbol that's thrown us off yet, which is cool, because I think this is, again, just the basics, and we're demonstrating, yeah, we know what these are. We can reason about this without looking anything up. No AI needs to tell us, and this allows us to move, like, fast, right? This is one of the benefits of having a strong mastery over the basics, is that once you master those basics, you can move sort of uninhibited. It's sort of like once you master touch typing and you don't need to look at the keyboard, you can get this super linear speed up. I won't say exponential, but you can get a nice speed boost. So it may take a little more time at first by learning how to type without looking at your fingers, but then the long-term benefit could be a lifetime of being able to type faster. Yeah. Okay, let's keep going. We'll try to go a little bit faster since we're already over the hour mark, and I don't want this one to go on too long. But this is just checking to make sure this is not equal to null. So this stream reserve pointer 1 is not equal to null. Reserve pointer 2 is not equal. Okay, so these are all just reserve pointers. These are int. Okay, int. Oh, it's interesting. I wonder where int 1 went to. Because, like, you know, this guy started at pointer 1 and 2 and 3 and 4. And then this one, this int 1 just starts at 2. Doesn't check 1. It's interesting. Okay, and this one does check 1. This enum 1 and 2. Yeah. Okay. Also notice that it didn't check if stream itself is not equal to null. So you could have a potential crash on your hands if this isn't null. Sorry, if this is null and you just jump directly to what it supposedly it has contained, because it might not be actually allocated. And then also, I would do this differently, just as an aside. Whenever you see like this 1, 2, 3, 4, whatever, there's this sort of screaming to be an array, and then you could just put this in a for loop, and just before whatever the number of pointers are, because like again, what does 4 mean? Like, that's probably just the number of things that maybe you need right now. But who's to say 4 is the number that is going to be needed for forever? I think that it could be that in the future you need 5 or 6 or 7. And so if it was an array, you just have a max here. The for loop automatically updates itself, and the code for checking on null never changes. So that's what I would do probably for all of these, is I'd make these all arrays. And then I would set the max size for each of the arrays. And then I would try to understand why this int 1 is not being referenced. That could be a bug. That is, yeah, especially because the pointer 1 is being checked and the enum 1 is being checked. That seems strange to me. Okay, next one, if test 86 ms byte b and prev mask is being right shifted 1 bit is less than or equal to 4, and prev mask being right shifted 1 is not equal to 3. Okay, so this is pretty cool, is now we're getting into, again, this is still basics though. This is not like an advanced thing. You don't need to know a whole bunch of things in order to understand the bit shift operators, which is what I believe is being invoked here. In C++, this could be either a bit shift or it could be a stream operator, but doing a stream operator inside of an if, it's pretty uncommon. You could do it, but it's probably not what they're doing. I think it is actually just a bit shift. And then the question is less than or equal to 4. So, yeah. You have the 1, 2, and the 4 bit. Okay, so in my head, what I'm doing is I'm thinking about the binary structure of this with prev mask. So I like the names, prev mask. It's saying mask, so it's a bit mask, I suspect, which is cool because it's helping me understand it just by having meaningful names. And then shifting 1 here. I don't always love the literals, but okay. And then less than or equal to 4. So you have, I'm trying to do this the way that, okay, so my video cam is inverted here, so it's not going the way that I'm moving. Is it going to show? Oh yeah, maybe it is. Okay. So you have the 1 bit, the 2 bit, and then the 4 bit, right? So the 1 bit and the 2 bit can both be set, and then it would be 3. And that's essentially, oh, and then you could also have the 4 bit set. So it's checking to see if it's less than or equal to 4. So if there are any bits that are being set that are beyond the 4 bit, or the 2 smaller bits are set and the 4 bit is set, then this will be false. So basically I think there's only a few acceptable outcomes here. All the bits are off. That would be a pass. Yeah, so prev mask, right shift 1 is less than or equal to 4. Okay, so all the bits are off. That would pass. The 1 bit is on. That would pass. The 1 bit and the 2 bit is on, or either of those are on. That would also pass. And then lastly, the 4 bit is on. And that's it. Those are, I think, the only states that this would be true in. So if I had my tablet, I would just write down what that, I guess I can just write it here. So it would look something like this. So that would be acceptable. That would be acceptable. Whoops. That would be acceptable. So all zeros, the 1 bit is set, the 1 and 2, because that'll be 3, or the 4 bit is set, and that's 4. That's it. There's no other cases, I think, that would allow that to be true. So this, no, that doesn't work. That doesn't work. Because in this case, the value would be 5. In this case, the value would be 6. In this case, the value would be 7. So those are the only ones that would be acceptable. And I suspect there's some particular rhyme or reason why that makes sense. I don't know what that is, but and that's why using the number 4 or these literals sometimes is not the best thing to do. And then we also want to check if okay, I take it back. Hold on, let's get way more fun. These are the only 3 that are acceptable now, because they're also saying that prev mask shifted 1 is not equal to 3. So they elided away the other one that we had, this one, which is 3. They're saying, no, you can't be that. So now they're saying only these 3 are available or are acceptable. Cool. Okay. Yeah. So why are these 3 the only ones that are acceptable? I don't know. We'd have to look at the code, but that's what I think it's doing. And what's also interesting, just as an aside, is the check here on test 86 MS byte B. I don't know. Yeah, we would have to look at the semantics of this, but I think that's a curious check to do in conjunction with this prev mask. This prev mask is checking specific behavior for this bit mask, but what does that have to do with B? Probably something, I hope, but it's not clearly intuitive or intuitive to me. All right. Now, I think that we could probably just, I think we have kind of the sense that we have some mastery over these basics. And maybe I'll just run through a couple other ones just to walk through. So this is the not equal to, this is the or, this is logical or, not equal to, logical and, more null stuff, equality, logical and, the not operator on this, what looks to be like a Boolean. Make sure that this option for standard out is off, so on and so forth. Just continue, not equal to, less than, nothing magical or different here. This is check on a specific array location, make sure that it's 0. Sure, that's fine. This is a cast to make sure that you turn this thing into the unsigned version of it. After you do this -1. Yep, that's interesting. In my head, there's some really interesting binary behaviors that can happen with this -1, especially if it's 0 and you do -1 on it, then the unsigned, yeah, has a, I think that's the max value, something like that. But this cast, I think, is quite important on this, especially if this value is 0 before you do the -1. Okay. A function call to make sure that's not true. More stuff. This is us just dereferencing this pointer and making sure that it's greater than whatever this is. More stuff that we've seen. This is pretty cool. Sort of. Okay, yeah. Okay. So I is not equal to null, or mem limit is not equal to null, or I is equal to null, or mem limit is equal to null, or in is equal to null, or in pause is equal to null. Okay, I see, yeah. Right. I was just trying to make sure this isn't a crash bug, but I think it's not. Because if in pause was equal to null, this would be true. And true ORed with anything is true. So if this were true, it would return true. If it's not true, meaning that in-pos is not equal to null, meaning it's been allocated, then you can safely dereference it, in theory. And so this is probably acceptable. You can probably do this. Okay. Then maybe they're trying to access these things inside of the if, and that's why they're checking on that they are equal to null. Actually, it doesn't quite make sense, does it? Oh, I bet this is an exit early condition. Is it any of these things, or this is greater than this? They're going to exit. Okay, let's just test this theory. I haven't ever looked at this code, or at least I don't think so. I think that's what it's going to do, and it's going to be an exit condition, or it's going to be somehow not continuing the function if this is true. Let's see what we get. This will maybe be our last little demonstration point for the evening. And please pardon the slowness of Mentor. Ah, yes, yeah. Okay, so that's what it's doing. It's a sanity check. And so if any of these are true, then it's going to exit. And the reason why I was able to see that is, the reason why I was able to deduce that it's an exit check is that it doesn't make sense to check these things this way if you're going to continue to do work inside of this condition. You would check the opposite. You would say I is not equal to null, memlim is not equal to null. All these things, they would be inverted, because then you know they exist, and then you can do work. So they're doing the opposite, and this is actually how I would write this code. Is like this as I think I was mentioning before in the never nesting. This is the way you keep the nesting pretty limited. Like, I actually quite like this code. This is probably Lasse Collins' code. I'm speculating, since he wrote most of it. And I like how, because of these exits, they keep the scoping relatively only a couple levels deep. Like, yeah, this is getting a little deep here, but up until that point, it's just almost like a single nesting level. Cool. I wonder what Mentor has to say about doing this. It's just trying to clean up the code a little bit. Yeah, I don't know, Mentor. I mean, I agree that this is. Yeah, I don't know. I don't. Yeah. Yeah. This one's better. I like this one. Oh, it's all void pointers. Ooh. Oh, whoa, this is a handle. Oh boy, okay. This would require some more thought. But oh, that's huh. Okay. I just noticed that Mentor seems to be checking in pause. Oh, it changed it. Interesting. Interesting. I think that Mentor's being overly safe here to try to make sure that this won't crash. That's why it does this additional check here. It's saying like, hey, in pause, you need to not be equal to null. And then I can do this check. And maybe it's forgotten that if in pause is equal to null here, then this will be true, and that this check won't be done. So what Mentor added here is not wrong, I don't think, but it is unnecessary in this case. So it's cool that Mentor's adding, like, this one's kind of tricky because This is why I got hung up a little bit on this, because I was looking for the check for not null, because I usually would want to see that before you do this dereference. And I think that's what Mentor's doing, is saying like, yo, before you do that, like, you should really check for this. And in general, I think that's good, but that's what this is doing, actually. So Mentor's not wrong in adding this as like a safety thing, but in this particular case, it's not necessary. I don't believe it's necessary. So I don't, Mentor, maybe you get an A minus here on the insights. Yeah, that's what I'm giving you. I think it's still right that you probably want to do something like this. Let's see if there's another. Yeah, I don't really love this one. Yeah. Uh, yeah, I mean, I think that's actually kind of what it's doing. It's pretty cool. Now it's just adding this logging message. But in any case, I think our original intuition on what this is doing, that this is going to go into an error case and potentially exit, is right. And notice too that that all came from just looking at that single line of code. Where was it? I have no idea where it was. No, it was somewhere in here. This one is that we're able to intuit this, and I think that's maybe the stopping point for this episode. Is I think these are the types of things that happen when you master the basics. Is you get a very deep and nuanced understanding for what's happening in a larger context without even knowing what that larger context is, because you understand why certain things are done, that you immediately, it's sort of like the analogy of the difference between what I call code understanding versus code comprehension or code intention. And it's this idea that if I ask you to go to the grocery store and buy peanut butter and jelly, and then you go to the grocery store and you buy peanut butter and jelly, great, you've done what I asked. Perfect. But a smarter system might come in and say, did you mean to add bread to that? And why is it asking about bread? Well, it's speculating that you might be making a peanut butter and jelly sandwich. So with that, thanks everybody. Hopefully this was a fun learning experience or something. And I'll see all of you next time.